Hi everyone, this is Caitlin. Welcome to the final practice exam. This is a fundamentals page that is also the cannabis page, and I recommend not using cannabis before trying this page because there's a lot of intricate little things to look for and you want to be sharp and on top of your game. We're going to start with we're going to list the 5 functional groups that are present in THCA, and then we're going to give the hybridization of the indicated atoms in the boxes. So do this one at a time. We have a nice little alkene right here. They don't have to be in any particular order. We have a nice little ether right there. We have this arene ring. Remember, benzene is not a functional group. It's got to be an arene. This right there is a carboxylic acid. Should be familiar with that condensed format for a carboxylic acid. If you have 2 oxygens and a hydrogen connected to or linked up there with that 1 carbon, once again, that's a carboxylic acid. The final functional group up here is an alcohol. If you were to list that as a phenol, that would be great. And I realized above I forgot the carboxylic acid part is important. The second part of it is hybridization. This guy right here has 1, 2, 3 atoms attached. So it's sp2, that's 3 letters, spp. This one right here has 3 hydrogens attached, 1, 2, 3, plus that carbon, that's 4 electron groups, or sp3. This carbon right there has a hydrogen attached, and it's 2, 3 more atoms. So this is another sp2 hybridized atom. This makes it a little bit easier to see that we have 3 different groups attached to this carboxylic acid carbon, and 3 means sp2. At first glance, this oxygen looks sp3 hybridized because we have 2 lone pair plus 1 hydrogen plus 1 bond of carbon. That looks like 4 electron groups. But it's important to note that this electron pair could come down and play into the ring using resonance. And so if that lone pair can be involved in resonance, it means it must be in a p orbital, which means it must be sp2 hybridized. So let me just do a real quick little thingy here. If we have a sp2 hybridized atom, then we have overlap of those sp2 orbitals with whatever atoms it's overlapped with. In this case, for the oxygen, we had a hydrogen on one, a carbon on the other, and then one of those lone pairs is actually in an sp2 orbital. And then the thing that's left over above and below that plane is the p orbital, and that's where that lone pair lies. So that's the hybridization, explaining a little bit more of the hybridization of that oxygen atom that was in question, and there's your p orbital. Moving right along to part B, we're going to find the pKa of the most acidic portion of THCA. I'm just going to do that first. We have a couple different protons that are highlighted, so we're going to find its functional group family. We see this guy is of a carboxylic acid, so it has a pK of 5. This is just like a phenol group because it is an OH group connected to the benzene ring. That has a pK of around 10. And then the rest of these guys, they're all just regular carbon-hydrogen bonds with nothing special going on, meaning it's not like it's next to a carbonyl like we've seen acetone has a pK of 19. So just any regular CH bond, like if it were CH4, that would have a pK of about 50. So the one of the carboxylic acid wins. So the approximate pKa of this compound is 5. We've already identified which is the most acidic proton. So here the next part is to add curved arrows to show the deprotonation of THCA with this generic base. We start at the base, which is electron rich. We end at the hydrogen. Hydrogen can only have 1 bond, so those 2 electrons have to be dumped onto the oxygen. The next part is to draw its conjugate base. So I'm going to leave out all the other hydrogens. This stuff is all the same. That hydrogen of the phenol is still there. And now we have a carboxylate group right there on that benzene ring instead of a carboxylic acid group. Last part of this multi-part question is to find 2 non-equivalent resonance structures. So one thing to try and steer clear of if you're trying to make a non-equivalent resonance structure is that we don't want to just move this portion. So if we just move that portion of the molecule, we would have an equivalent structure. because these two guys are equivalent to each other. You have one single bond to oxygen and one double bond to oxygen. The other thing that we want to avoid that would make it, right, so these are equivalent. Another thing that would do equivalent resonance structures if we took, just focusing on the benzene ring, if we moved everything around like that, then we would get an equivalent resonance structure where the double bonds are just alternating in a different way. So that means we're going to do some other stuff. Instead, we're going to use oxygen's lone pair. Let's kick those right on down to make a double bond here, and we'll take those 2 electrons and dump them onto that carbon. They're still going to have a 6-membered ring. It's one strategy for drawing resonance structures is to start with the full single bond structure first, because that can't change, and then add in other pi bonds and other stuff that hasn't changed at all. And the stuff that has changed is now the double bond to oxygen, lone pair on that carbon. Whenever oxygen has 3 bonds, it has a positive charge. Whenever carbon has a lone pair, it's negatively charged. So let's keep that direction. We'll start at that lone pair and we'll end at this bond, take that pi bond and end at that carbon. We'll now have 6-membered ring, start with that same strategy of the single bond structure all being the same. Then we'll go in and add the pi bond stuff, these guys, and that means that this is going to be positively charged, this oxygen would be negative. And the new stuff, the different stuff, is when you have now a double bond here, lone pair down there. And these are all non-equivalent to each other and to the original conjugate base. First of all, because you have more charges on this structure than you do on this structure here. And the difference between the second and third structure is the distance between those charged atoms. Here they're 3 atoms away, but now they're 1, 2, 3, 4, 5 atoms away. So those are going to be non-equivalent. Last but certainly not least is the decarboxylation of THCA. This is a process that's initiated by heating the oil or flour that then, as a net process, removes the carboxylic acid proton, or the carboxylic acid entirely, and it turns it into just a CO2 molecule. And what we have in place of that is a hydrogen. I'm just doing some like big picture stuff, noticing that this hydrogen was already there in that middle step. And that's going to be sort of the beginning process, or the beginning of our process to see how decarboxylation occurs. We're going to add curved arrows to explain the movement of electrons from a base to a proton. So you're given some information here that you should be starting at the base and ending at the proton. That is given. I'm going to make a list of bonds broken and formed because there's a lot going on here, but I do want to highlight, because highlighting is fun, that this is the only region that's changing in the first step. Nothing's happened to the carboxylic acid group aside from the fact that I just made that an OH, whereas this is an OH with a line in between it. They're exactly the same. So let's make that list of bonds broken and formed. What bonds do we not see here? And what bonds are new here? So we have this oxygen-hydrogen bond, which is no longer there in the product. That's an OH bond is broken. We have oxygen-carbon single bond, carbon-oxygen pi bond. So that guy's going to be formed. Move this a little bit. We have some other things. We have this double bond is now a single bond. So we're breaking a carbon-carbon pi bond. And then the other thing is kind of already highlighted is the new hydrogen. So we should be forming a new carbon-hydrogen bond. Once again, we're given that nice little hint that, I could have kept him, that nice little hint that the arrow pushing starts at the base. So I'm going to do just that. I'm going to start at the base lone pair, and I'm going to pull off this hydrogen. This then kicks these electrons. What you might think is that it kicks it onto the oxygen initially, which might do for a second to explain breaking the OH bond. But we know that we also are trying to form this carbon-oxygen pi bond. So let's go ahead and make this a little more efficient, a lot more efficient, make it happen in one step. Kick these electrons down. So boom, we form the carbon-oxygen pi bond. Now we have too many electrons around this carbon here, so we need to ditch them a little bit. And we're going to ditch them, and we're going to have them pick up that proton 2 check marks with 1 arrow. We broke the pi bond and formed the carbon hydrogen. Cool. Next part is the actual decarboxylation process itself. The first part is just an isomerization reaction, a really specific one that we learned was keto-enol tautomerization, and now we have this ketone that we got from the enol. But that part's already done. We are going to make a new list of bonds broken and formed. I do this down here, what bonds are broken and what bonds are new, what bonds are formed. Notice the hydrogen is there in both cases, so I'm going to erase that because that could be distracting. And we're going to note the things that are different. We went from having a carbon-oxygen pi bond to a single bond. That means we had to break that guy. The other thing in that highlighted area, we formed an oxygen-hydrogen bond. We go from having a carbon-carbon single bond to having a carbon-carbon pi bond. So we're going to be forming that guy. And last part, biggest deal, is that we no longer have this whole chunk. That's gone. We did the breaking of the carbon-carbon single bond. Huge deal. Something that could be helpful as well to really keep track of all the good stuff is to note that carbon dioxide's Lewis structure is as follows. And that way we can really track where that carbon went. So this carbon and that guy, those are the same. And you can see that the carbon goes from having 1 single and 1 double bond to having 2 double bonds. So we actually are going to be forming a carbon-oxygen pi bond. And then you can also see that, oops, put that guy back. If we focus on the oxygen connected to the carbon of what will become carbon dioxide, is that we should also be breaking an OH bond. And I did my best to color this as this is like the purple carbon, because obviously there's other carbons in the molecule. Okay, there's our setup. Very good. Let's, once again, we're going to start at a base, end at a proton. Bases are electron rich, protons are electron poor. We start at that base, pick up this proton. Eventually we're going to get to that proton, but that's the very end. We're going to pick up that proton and kick these electrons over. What we've done in the process is we've broken this OH bond and we've formed that carbon-oxygen pi bond. Now there's too many electrons around the purple carbon, so we're going to kick those electrons over. This is the big deal of how the bond actually breaks. They just go ahead and swim themselves over to reform this aromatic ring. That's a big deal, is reinstating aromaticity. So here we're going to be breaking the carbon-carbon single bond and forming the carbon-carbon pi bond. And last but not least, we're going to have to break the carbon-oxygen pi bond to pick up that final proton. Breaking the carbon-oxygen pi bond, forming that final one. And that's it. That's the decarboxylation process. In order to actually make it work, once again, it has to go through this tautomerization process, and then the decarboxylation can occur. I hope you enjoyed, and we'll see you on the next page.